Over the next few years, every business is going to either become an AI first business or be disrupted by one. But what does it mean to be an AI first business? We all use ChatGPT, but how can you apply AI within your company to become an AI first business? It starts with an AI powered office. We made Rome to make it simple for any business to become an AI first business overnight by incorporating a company visualization with presence, drop-in meetings, video conferencing rooms in a theater with AI-powered meeting notes that can trigger agentic workflows where AI agents can begin to do basic tasks like scheduling, sending emails, and farming out information. With Rome, your business can become AI first overnight. Nobody knows what the future holds, but I do know this. It's going to be built in the office of the future. It's going to be built in Rome.
Yeah, welcome everyone. Thank you so much for joining our session on collective intelligence today. We started this program recently, and it's really a global learning space designed to give you direct access to education at the frontier of AI. And this session today is made possible thanks to our sponsor, Rome, the video that we just saw, and our amazing partners at Maven. Today's sessions is actually about what AI teams get wrong about vector databases and its significance in AI. And we're very lucky to have Doug with us today. Doug is, yeah. Doug is a leading consultant in search technology and relevance engineering and an instructor on AI-powered search at Maven. He has built hybrid systems combining lexical and vector retrieval and designed LLM-driven quality programs for e-commerce. Doug has led machine learning-powered research at Reddit and Shopify and has hands-on experience with leading vector and search platforms, including Pinecone, Weaviate, Elasticsearch, OpenSearch, and so on. And today he will share insights on how to evaluate vector DBs, what to look for, and how to build systems that are scalable and future-proof. So welcome, Doug. Very excited about our session today.
Yeah, thanks for having me. Let me share my screen. Everyone see my slideshow?
Yeah, looks great.
Great. Awesome.
And we're going to have a Q&A session later, so stick around and the stage is yours.
Yeah, so welcome everyone. I'm going to talk about my perspective on vector databases, what AI teams get wrong about vector databases. And I think I see a lot of anti-patterns, misunderstanding. A lot of people are sort of rapidly coming into the space. And if you're building a RAG application, you hear, well, I need a vector database. So I want to talk about what that means exactly and what you probably really need and what you need to think about when you're implementing this. This talk could also be called like what AI teams get wrong about vector search, because how you choose a vector database is very dependent on how you're building vector search. I have actually two courses happening right now. Lisa mentioned AI-powered search. There's also my search I've done now once before, and it's getting better on its second run, is Cheat at Search with LLMs, which is all about using LLMs to improve information retrieval. And that's anything from query understanding to content understanding to LLM as judge. So if you're interested in this, what I talk about today, there's going to be a lot of great content in this class. So definitely check it out. With the commercials out of the way, I would just talk today about how we got to where we are today, vector databases, with like a focus on RAG specifically. And then sort of like what they're usually missing and the questions we should ask when we're building a vector or a search system, especially for AI, and what we should be looking for in terms of functionality and capabilities, not just in the vector database, but what we actually need to build ourselves that the vector database should enable. It's not going to do a big comprehensive like table or comparison of a lot of vector databases. There's so much data out there, and there are actually a lot of great tables. And honestly, my experience is colored by the projects I've been on and the ones I've worked on. So I haven't done this kind of extensive study. They're all doing great work out there. And one of the things I'm really grateful for is the fact that there is so much money being put into the vector database space that there's actually innovation that's happening in information retrieval that wasn't happening necessarily 5-6 years ago. So it's a really exciting time. So most people probably on this call, I'm guessing many of us know what an embedding is. So just as a quick primer, you can see here, I've got a bunch of people and movies. They're just scattered around this like 3-dimensional space. And what if I want to, there's a lot of value in trying to move things that are similar closer to each other. So I might have this, what we call triples of here's Doug, here's something he likes, and here's something he dislikes. Tom likes Sense and Sensibility and dislikes Star Wars and so on. Well, if I tweak all of these points to be a little bit closer to each other in 3-dimensional or really very much higher dimensional space, you can start to cluster things that are similar together without necessarily knowing the relationship between everything and everything. Maybe Doug gets closer to Star Trek, Naked Gun gets closer to Star Trek, and through the transitive property, we kind of start to learn relationships between things in this space. What's near Doug, what Doug might prefer, and what's far from what Doug might prefer. Which users are most similar to Doug, which users are less similar to Doug. So that's a really convenient thing. And the classic way of doing this, and this is really sort of like what Word2Vec does, is if we get an embedding for each of our things, literally starting to a random location like we did in the couple graphs ago, we literally can, people call this deep learning, but more or less it's just moving the dimension at a time a little bit closer and a little bit closer so that the similarity, in this case, similarity just means distance function. If you remember geometry, there's lots of ways of imputing the distance between 2 points. And similarity in this case is sort of like the higher the similarity, the closer they are. So we can compute that mathematically, and you can go and look for things like cosine similarity or angular similarity, all of these things, which are ways of measuring whether 2 points are close or far from each other. And we literally can just move points closer or farther from each other by tweaking one of the dimensions. In the x-axis, we move Doug a little closer, and so on. We just repeat this over and over until we can't really make things any better. And so we get an embedding stable, of course, that's like Doug is close, and these are, now we're looking at them as 3D points, not as on a graph, where Doug is close to these movies, but he's pretty dissimilar from these other movies. And there's a lot of value once we add more dimensions. Of course, 3 dimensions is going to be better than 2 dimensions because I can have more freedom in how things might be similar or dissimilar. And nowadays we go up to 768, 2096, or 4096, 2048 dimensional vectors. And we call these dense vectors because they don't have millions and millions, and nearly every value is filled in. So these are just points, and we're moving things that are similar closer and dissimilar things farther apart. And that's why we say embedding, because we're embedding in the space. So of course, we might have someone new that we've never seen before, Bob, come along, and we don't know where to put Bob in anything. We say this Bob is outside of our vocabulary because we often think in terms of words. Now we could get a bunch of Bob's preferences and retrain this whole thing so that all our points are close and far as they should be. But often, and this is what we see a lot, we have ways of encoding users or sentences or movies or products into an embedding using their attributes. So we pump a lot of attributes in to a deep learning model, and we do the same thing. We see how, is it near or far? Or do we need to tweak things closer? Well, we don't just tweak the embedding, we tweak what creates the embedding, which becomes a function actually now of the user's attributes, maybe stuff like what was their favorite movie, what was the last movie they watched, what age they are. All of these things can help us actually predict an embedding for Bob and put Bob in the space of the embedding space. And this is really the revolution we're living through in information retrieval and search. It's become so ubiquitous. Many people may know you can go to Hugging Face and get an embedding model that can take all kinds of things. Images, there's embedding models for images to terms, search queries. Users can have embeddings. We can build our own embeddings, but a lot of times, it's 90% of the time, people are just going off to Hugging Face and getting an embedding that's pre-trained on whatever data they care about. So the other big revolution that happened, so not only can we have an embedding, and not only can we learn an embedding as a function of the attributes of the thing, another thing we can encode is actually each state in each token in a piece of text. And transformers essentially, using the attention mechanism, give us an embedding at each position that captures something of the semantics of that location. And at the very end, we have the CLS token, and we have an embedding for the entire passage, right? And that's pretty amazing. So people have gone through and figured out how to do deep learning and build an encoder that can encode the meaning of an entire sentence based on similar patterns of what we see in training data and how language works. And this is sort of like around 2000, we were really making headway on what had been a really gnarly problem of question answering. We have some question, what is the best recipe for cream spinach? And we have some sentence, a yummy recipe for clean spinach and all, blah, 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 blah. And we can see that this chunk is close to this chunk. And this isn't necessarily a talk on how transformers work, more to say this is just the reality that we live in now, but I definitely recommend if you're interested in this to dig into that. So now we get closer to actually having embeddings and embeddings of the database, because you can imagine if we break up some text, maybe just by paragraph or into sentences, now we're going to have millions and billions of these chunks. But we're going to have a question we want to ask. And the first thing we're going to want to do is say which of these vectors, this chunks really, this vector, is closest to our question. And this is exactly the same as graphing the movies and people, except in this case, we're graphing how close chunks are to each other. So we have a new type of data structures problem. If we have, here we're showing 3 dimensions, which isn't actually that hard, but in 768 dimensions, how do we take a query, this red X here, and gather results that are closest to this red X? And there's been decades plus work on this. The first thing people obviously saw was, hey, I could just cluster these. I can see all of these belong to a cluster, all of these belong to a cluster, and so on. And I can say, oh, my query is actually close to cluster A, so I'm only going to scan and retrieve Star Trek Doug Naked Gun. The other thing, of course, you have to somehow figure out the right way to get good clusters and balance all the clusters and all of these things. So there's challenges to this. And the other technique people tend to use is graphs. So people may have heard this concept of a hierarchical navigable small world, or HNSW graph, that is the data structure behind a lot of vector databases like WeVA or what Elasticsearch uses now. And we basically connect all the neighbors together, and we see sort of like a map of the space. And you can think of it a bit like a roadmap. So if I'm here and I want to see, okay, who's all the neighbors for this X? Well, I would probably maybe use, if this was actually a real 2-dimensional map, I might use a roadmap to be like, oh, if I go down this road, I can collect all of these these homes or parcels or whatever into my candidate set. But I might be in a place where like the nearest neighbor is actually really far away. So I'm going to have to take a highway. A highway is going to connect me over here. So you can really cleanly have like these dense areas that are tightly connected, but also like middle of Wyoming or wherever that are like real, your neighbors are actually really far apart. And people combine these things. For example, a lot of higher scale systems um, will have clusters that sort of shard up the graph so that you can quickly navigate to a part of the graph and then do your HNSW within that piece of the graph. So this was all 2020-ish, pre-2020, and there wasn't really much out there in terms of vector databases. There were libraries. So there was people where remember Eric Bernhardsen had Annoy, which was very popular, which used trees actually to map the space. Phase and HNSWlib were coming out, Phase from Facebook, NMSlib, another one. And so there are a bunch of these libraries that were coming out, especially from big tech companies, because big tech companies actually had enough data to have embeddings for everything. But we sort of had this space where I could begin to embed anything because I have all these models from Hugging Face and other providers. But what do I do with them becomes a real pain point. And at the time, it just felt like when vector databases started to come on the scene because they weren't necessarily thinking about OpenAI or ChatGPT or RAG or anything. It's literally like we have question answering. We can embed anything. We can make users to movies or users to product embedding models. We can build semantic search. We can do image retrieval. We've built embedding models that connect anything to anything through a similarity space, but the data structures aren't there. And so we actually start to get vector databases as more like full service databases that you can index data to. Maybe they're hosted quite often. You can retrieve data, get your top end data from them, and helping to solve a lot of these problems. And this is, by the way, Ito. Ito's a buddy. He's the Pinecone CEO, which is another great vector database out there. So yeah, and then the other thing, we sort of had this parallel world of traditional search, and I worked in this world. And it seemed like they were fairly focused and consistently on maintaining the traditional sort of search paradigm, which is based on token matching, like literally string matching, like a very efficient way of taking apart text, tokenizing it, and then finding documents or whatever that also have the same tokens as a query. And you may have heard of scoring techniques like BM25 and other kinds of lexical search. And the big question at the time and frustration for me and the community that was working on search is it doesn't seem like these search engines really get it. They're not really building this at the time. They sort of need a kick in the pants to really care about this. And this is why the opening of vector databases became so prominent, because it wasn't really coming to Elasticsearch or Solr for a lot of different complicated reasons. I will say that all credit goes to Vespa.ai, which is a different search system entirely that at the time was very focused on information retrieval. But I remember at the time, pre-2020, information retrieval wasn't seen as like a big growth market. And now all of a sudden, it's this massive thing that's going to take off and conquer the world. And you can see there is this completely different sort of like historical flow that we went through. At one point, we basically were discovering different ways of scoring things based on whether a token matched from the query to the document. And there was an entire science about how you actually score that, what statistics should you take into account. And then eventually we learned that we can use ML models like learning to rank to score these results. So learning to rank is basically a way of taking a combination of different factors and combining them into a ranking function. But we were kind of on this path, and this sort of like historical nice flow is about to get clobbered because there is a completely different world of information retrieval, like I've just talked about. Honestly, going back to the 1990s, where we started to do things like matrix factorization, where we turn a big matrix of like, if you create a matrix that's like every query to every document and put a 1 if it's relevant. Well, if you can actually do matrix factorization to get a query embedding. We didn't call it embeddings then. It was just a vector from the mathematical sense of vector. And we didn't have any way of storing or using it other than to turn it into sparse representation. And when I say sparse, I really mean like see that the word cat is very similar to kitten because they tend to appear in similar documents, or they're all both appear in relevant documents for each other. So we went through this phase, and these are all just different things you can query and you can go learn about if you're interested. And it seemed like for a while, like I said, this whole space was moving. We had great tooling for ML engineers, like new development innovation. If you were down here and you were like an ML engineer and you were forced to jump into like Elasticsearch in 2020, it was just confusing to you. It's almost like a very 2000s era open source mindset of having like, a lot of Java and whatnot. Whereas up here, it was just like people felt very comfortable just pip installing, importing and Hugging Face model, playing around with some vectors. You can do dumb vector things in like NumPy in memory, and they would hit some wall and be like, oh, I actually need a vector database because I have too many vectors to index. And there's a lot of VC money, right? And it goes well beyond search. So search recommendations, really anything. So 2022, ChatGPT drops, and we sort of have this moment where all the ML engineers, I talked about transformers, had this sort of existing question answering experience from their history. They're like, oh, I know how to I need to inject some new context into my LLM. I know how to do this. I've done question answering before. I've played with BERT. Let me grab the query, get an embedding for it, and just retrieve the relevant chunks, just like I'm doing question answering. It seemed very connected. And so that's honestly where a lot of RAG gets started, is like assuming that our main task is question answering. And it's not a bad assumption, but it does break down. And so now all the vector databases were waiting in the wings, and we sort of had a vector database bubble where they were all ready to rank your chunks, right? And now we have this case where the vector database is like in 2022, it was like on fire, fully SHT, and everyone is like piling on at like an insane pace to build whatever AI application they're building. And still down here, they're kind of just starting to get a kick in the pants of like, wow, we really need to focus on this space. So that's the context of where we are and how we tend to think about historically vector databases and the assumptions that we go into when we're selecting one. So how does this actually work in practice? So you might have a user that comes along, hi, can you tell me the 2025 financials for XYZ company? And there's like one chat turn where the LLM formulates a query and we get some context back. And we assume that there's actually a chunk that beautifully captures the meaning of the query, and in this pure platonic question answering sense, and then everyone's happy and we get the information we want. And what also happens is we tend to build up state. So we have this previous query that is almost like a state that we're carrying along. And we not just pass the full context, but we actually ask the LLM, can you adjust this query to bring in the additional like content and whatnot. So we take this query, we tweak it a little bit, and we go and you generate a new query, 2025 financial XYZ content EU. So the reason we do that is because this context over here on the right can be like start to get really verbose and complicated. We need to maintain this like current working space of an information need and pass it in every time and regenerate the new query. So we get a new query, XYZ, 2025 for XYZ company in EU, and then we hope to match a completely new chunk. So we go through, this is just last query context, LLM. This is like every chat turn. We get a new query and we get a chunk back. So the first problem starts to appear that it's not just chunk similarity, because we have this realization that a lot of times our data isn't necessarily represented as part of the chunk, but as some metadata attribute. So maybe we have a report from 2021 that's got a timestamp on it. Maybe we have something with a region or a stock price. So we start to see that we actually need something closer, not just vector similarity. And this is the very first thing and one of the most important things to evaluate your vector database on. You don't just need vector similarity. Like at one point, all the nerds got excited about building vector databases because it was a fun, hard data structures problem to just focus on that. But in reality, what you need is a vector search, but within the context of some filters. So here you have company XYZ as a filter, maybe year 2021. And notice how I'm changing the nature of this query to be more structured. And this is a big thing I talk about in Cheetah Search with LLMs. Like basically what LLMs let us do is to think about our queries not as just a question that is a chunk that's going to match some other chunk, but LLMs, especially increasingly with tool usage and structured outputs, they really let us maintain consistent structure and enforce a sort of like JSON structure in a way that's useful, although I see I'm missing a quote here. And that's really useful because we can actually like enforce like a schema, like a tool or a backend or a function that's going to get called or something like that. So if we do need to add filters, so we see these dotted lines, maybe we filter something out. And let's say we're retrieving the top three results. Well, what do? Do we go and just like, okay, I only got one the first time, let me query the database again, maybe with asking for a higher top K, hoping it's like if I troll the ocean for more fish, maybe I'll catch that prize tuna after throwing away a lot of not as exciting tuna. And that's a lot more work. So do you keep going back and expanding? Or if you have this is what TurboPupper does. TurboPupper is a pretty hot up-and-coming vector database. You could also build, if you have a sort of cluster system, notice how they have the queue here is query. 0 is like one cluster, 1 is another cluster, 2, 3, so on. In this case, they have a filter that's like a sort of file path. And I think they're searching for foo/source in this blog post. Well, they can just, if you have a cluster, you can pre-filter down to the clusters that you care about as a first pass. So you have options, and depending on, and then Elasticsearch and Weaviate do this thing called Acorn1, which is what you would do for graphs. So graphs, what you're doing is you're just if you're doing a query of a graph, you're starting at you're walking a graph. So I'm starting at wherever the closest thing is to my query is, and then I am trying to like go to its neighbors and see if they're actually close enough or closer than wherever I started. The starting point could actually be a random place in the graph. And at each point, you're saying, like, is it satisfying my filter? In this case, this is actually from a live coding of a vector database I did. You sort of see, does the filter, is the filter satisfied? In this case, it's a color. And Acorn1 literally just says, well, as I'm scanning the graph, I'm going to look not only at the neighbors of the current node I'm examining, but their neighbors, and continue to gather more results. So you're like, it's sort of like casting a wide net as you scan through a graph to sort of like gather candidates. Qdrant does something different. I know some databases will actually do something. Qdrant actually does something into a graph that's similar to what TurboPuffer does. So you really have to look and dig in the details. It's not just I do HNSW or I do this clustering approach. It's this whole like what data structure is actually used when you're doing filtering, because it can make a dramatic difference on the performance of your data. But also, what kinds of filters can you do? Can you do metadata filters? Can you do full text filters? Like, can I say like take this query and see if it is 100% match for the title and filter that and then score based on vector similarity? Like, these are all open questions that you really have to figure out. And every vector database they all start to look the same when you're like, oh, let me just throw some vectors in and get some vectors out. But this is really where they start to be very different from each other. Because I'm almost certain that you will need to filter before doing some kind of vector similarity. So the other thing that comes up is we're all excited about embeddings and vectors. But there are many kinds of similarity. Like there's geosimilarity, there's numeric similarity, like literally how far is the popularity from a desired popularity? So if 100 is the best popular, how far are you from that? And sometimes that changes really fast in a way that you could never like retrain an embedding very easily on. So there are all these like numerical attributes that you have to care about too, and their similarity. And tools like Elasticsearch, traditional search engines have had many of these types of different indices for a long time. And then boring lexical search still matters. And that's something I want to talk about because it's an interesting thing to think about when you're working on your vector database. If I'm searching for Jimmy Carter, I will want to occasionally still go and get the exact matches for Jimmy Carter or things that match that term exactly. And there are reasons that embeddings don't always capture this well, which I'll talk about. One thing I want to warn people against, because this always comes back, is don't just tack on a vector database off to the side of your search system where you have like lexical results from one group and vector results from another. And I'll talk a little bit more why that is in a little bit. I actually have a blog article on RRF. RRF is this type of interleaving that you can do between different search sources, reciprocal rank fusion. But there are reasons that you want to avoid doing those kinds of things. Yeah, so BM25 is still useful. And what I want people to think about when they think of BM25 is it's really like what it's measuring it's a direct measurement of if this term or concept or whatever matches, that's the key thing, matches, then how much is this document about that term that just matched? And that's where we start to get into statistics like term frequency. How often do these words occur in this document? The document length. If it occurs once in a tweet, that's way more important than once in a book. And document important or term importance, really, which is Carter here is probably a rarer term than James. So if we see Carter matching a lot, then that is going to be a more important match than if just Jimmy matches. In the end, it actually turns out that when you go back, and you might have seen in my timeline back in the history of traditional search, in the 70s, people talk about the vector space model, and that's exactly because people see these queries and documents that are lexical, that are just literally like a term. How many times does a term occur in this document? That's a vector too. And you can see here, like document 1, the Carter dimension and Jimmy dimension are high. Our query is just a 1 for Carter, Jimmy, and a 0 for everything else. They're called sparse vectors because they're almost all 0, and they're very large. So they're the size of our vocabulary. It's every term in the English language. Of course, under the hood, they're not represented this way. They're represented as like a dictionary. But that's where the concept of conceptually they're sparse vectors. And sparse vectors, we can play little games like making things synonyms, like manually, this is like old school search, making James a synonym for Jimmy. And we credit that to Jimmy. And back in the day, a lot of my consulting was dumb things around synonyms when I would help people with search relevance work. And these days, what's really cool is, remember, we can take our transformers, and for each of these positions, we can actually look up, given this embedding, what other terms are likely to go with this term. So we take this embedding, we look up in our word embeddings, what else would go here? Spinach, greens, collards, creamed, creamy maybe. And you can see here, we can actually use our transformer model to make our sparse vector smarter. And this is, you may have heard this concept of SPLADE, but SPLADE is a really revolutionary idea that helps people think more deeply about sparse vectors and how they might include them in their search systems. And you could see that too, like maybe if we had Jimmy Carter was an American politician, a humanitarian, well, this is interesting because if you just looked at this from the perspective of the word he, I'm not going to make a synonym from he to Jimmy in the sense of mapping it globally across my corpus. But in the context of this sentence, you can see a transformer might be able to pick that up, that Jimmy actually goes here, because we know what it's referring to. Yeah, so we can add that reference to making it 6. And a lot of traditional search relevance is honestly like working with the index to make this sparse similarity closer to what our users expect when they're closer to what they expect when they look at a relevance ranking. Like they would see, if you said he a bunch to a Jimmy Carter thing, but another article said Jimmy Carter a bunch of times, they might actually prefer the one that said he maybe a bunch of times because it's indirectly referring to Jimmy Carter, very much about Jimmy Carter. And of course, we could learn this in embeddings. I wish there was a Wikipedia article on me, but there's not. But let's say there's query Jimmy Carter, we know that we can build a sort of query to document kind of thing where we can find a Hugging Face model that might do a query document thing. And we might embed these closer together. So we might be able to get away with embeddings for everything. But there's a problem with that. And this is why we actually reach for sparse solutions. The first one is embedding collapse. So what happens all the time, and I use this example from fashion search that's happened before. We're like, if you search for, I've been surprised at an image recognition algorithm, embedding algorithm. If you search for red shoes, blue shoes can be extremely close to red shoes. And it's really surprises you because as a user of this solution, you're like, these blue shoes should get nowhere near these red shoes. And the reason for that is whatever image embedding algorithm, if you look at just generic clip or whatever, it is like using the entire space of images. And I only care about this little corner of fashion. And because all of my stuff only exists in this little corner, everything is going to be really similar to each other. And all the similarities collapse so that red shoe and blue shoe are like 0.01 different from each other when I search for red shoe. And that can really surprise people, especially when it can be the case that your domain may also just be not as represented in the training data. So you get these kind of like strange clusterings that happen in your data that can kind of throw you off. Of course, we could train our own model, but that assumes we have skill, we have time to maintain model, and that's completely up to you if you think that's something that you want to do. And embeddings, another way of thinking about embeddings, they're actually a compressed view. They're a lossy view. So 768 dimensions, floating points is somewhat of a compressed view of 1 billion dimensions in a sparse vector. So because of, if our training data is not complete or whatever, it can make mistakes. We can have problems. So if we're training it ourselves, we have to be really careful about that. or if we're looking at a embedding model, we're taking off the Hugging Face, we have to be careful about that as well. Like it may just be a compressed view that's you think about it, if there was a JPEG and for some reason it was only biased towards the outlines of things because that's what there's a JPEG and a bitmap. And we wanted to sort of compress the JPEG based on some training data. You might imagine like one compression of a JPEG might be to only show black and white outlines of things. Well, if something like color is really important to us, it can be lost because we are compressing this data down. And so if what we care about isn't represented in the training data, then that can be a big problem. And the other thing the actual big challenge for all of this stuff is getting, if you are building your own embedding model, is getting really good training data of, okay, someone searched for Jimmy Carter, what is actually relevant or irrelevant for this query? And that's actually probably the really hard problem behind a lot of searches, getting really good training data, even with LLM suggestion, like good stuff. So when we think about this stuff, you care about sparse data when you're picking a vector database. Sparseness is about, like I said, aboutness on a match, like how much is this text about the match. It gives you a lot of flexibility and sort of like a default assumptions at query time and index time that just sort of mostly work out of the box without you having to train much. And it's useful for obviously a hard filter exact match. All the reasons for dense that I just gave. But the other big one that I didn't have a specific slide on is like, there's no specific cutoff between a match and not a match. So that example I gave of red shoes and blue shoes, well, often there's like red shoe. If I'm searching for red shoe, you'll have red shoe, red shoe, red shoe, blue shoe, red shoe, blue shoe, red shoe, blue shoe, blue shoe, blue shoe. It's there's not a clear way of necessarily always cutting that off. And actually it can be very challenging to know what floor to set a vector similarity at. So yeah, how flexible is your database? How flexible is your BM25 similarity? How flexible is the tokenization behind a lot of this stuff? And that's where I say waves vaguely at what Elasticsearch does, because controlling tokenization is really about how you control sparse vectors and how effective BM25 is going to be by defining that Jimmy and James are synonyms, or how you take English words back down to root forms or don't take them to root forms and that kind of thing. And then when we think about an actual search problem, behind an actual search problem, like before I had like filters of like year and I believe company name. There are a bazillion other types of similarity that happen, and many of the similarities aren't things like vector similarity or BM25 or numerical similarity. It's actually like, no, I am a user. I understand what cool is. When I say temperature cool, I mean roughly this temperature range, and I mean this one is a little bit closer to this one. Now our backend or vector databases don't have temperature similarity. So we, as people building search solutions, are required to define that or build that. And there are lots of ways to doing that. Obviously, there are ways of doing sort of a curve that multiply the temperature by the desired temperature and getting some like so close to the desired temperature is like better, and as you fall off, it gets like exponentially farther apart. There are many ways of doing these things, but it's not all based on vectors. Recency is another one. Popularity, those are all numerical ones. Name similarity is interesting. Doug to Douglas, but maybe not confusing first and last names. A lot of what we do as search practitioners is working on these like domain specific similarities and actually building systems backends for some type of similarity. So color, pink is closer to red, but purple is probably farther than red than pink. So all of these are actually similarities. It's not about filters and things. Skills, computer programmer is similar to software engineer, but that's dissimilar from electrical engineer, and all of those are even more dissimilar from line cook. So that's actually what we do as search people. It's not about like matching things. And we can do all kinds of like hacks. A long time we've built these sort of similarities as sparse vectors. For example, Paris in December, you might say it's cool, cold, lukewarm. Someone's going to correct me on this. Antarctica is going to be freezing. And you can see all of this is almost like the term frequency. It's like a sparse vector. If my query is like, I want cool, well, maybe I have this, I can match and I'll see Paris in December will rank higher than Antarctica. If you read my first book, Relevant Search, this is a lot of the hacks are hacking things into sparse vectors to build your own type of similarity for your domain. And then finally, as a last point, the other thing that you need to look for in a vector database is its expressiveness of its query DSL. So we've spent this entire talk talking about similarity. Similarity is only the building block. Similarity is not the final relevance or ranking function or scoring function, which is used interchangeably with ranking function. We take a function of a query and document. Well, maybe for whatever reason, we look at our test data and it's like, if I take an embedding of the query by the title times the date times popularity, that's what I should do, and that seems to solve my users' problems. And all of this is grounded in amazing evals, or at least some hacky evals that you put together to like believe in this. Or maybe you have this thing, if all the terms match between the query and document, then maybe rank on the embedding, otherwise ignore the document. Or you have a straight linear function. This is straight up like BM25 boosting. Like we'll figure out a title boost, maybe that's 10, description boost is 2, and we multiply these and we add them together. And when you look at something like Elasticsearch or even SQL and PG vector, Weaviate has a rich query DSL. Like all of these systems, Vespa has a really rich query DSL. All of these systems have query DSLs, and it's like people get so focused on like some specific way of doing similarity, they don't necessarily evaluate like, can I program the scoring function I need into the query DSL? And a lot of times, how we do this is completely dependent on the query itself. If I want latest news on XYZ company, well, my LLM might route to a specific backend that does something like this. It's supposed to be query, it's supposed to be company name to document times the recency. So maybe this is some kind of like specific thing looking for company names. I think that got messed up. Or I might have like different strategies that I pull back. So I might use what I call different retrieval arms for getting different candidates back from the, not just like one ranking from a vector database. I need to be able to pull back multiple rankings based on like, I'm 75% sure set 1 is more relevant, but I'm 25% sure this one would also be good. And I need to be able to express these specific to the use case. And we could, of course, one thing, and a tool like Superlinked, which is another cool thing that's come out recently, can help you do this. You can fine tune a lot of these things into a single multimodal embedding. But of course, see our earlier discussion, that's not necessarily the most straightforward thing to do in terms of getting training data and building. But you should totally do it if that's like what your comfort level is. Or you can think about leveraging a rich query DSL. This is TurboPuffers query DSL. You can see here it lets you do multiplication, summing things, and some of this may be ChatGPT hallucinated, this specific example. But you can see how it might rank by things, and go over a certain 100 top K. And this might be specific to a specific use case that I have for my example. And that's actually, yeah, basically the same thing. It's actually why every one of these things, when you do a search strategy for a specific, we might think intent or type of query or information, type of information need, it's actually, each of these is a hybrid strategy. Maybe product by name or news article by date and topic. We're usually combining vector and lexical together. It's not like we're not pulling some results from this and some results from this. If we could design this, I would put one of these database things for maybe the like product name search that I showed before, one search strategy and another one for second search strategy, and so on. That's specific to my intent. And then you're turning on and off different ones depending on the user's actual intent. It's really more or less everything's converging so that all these systems are becoming more and more similar. And now the new hotness is vector databases are turning to search engines by adding a lot of these capabilities, and our traditional search engines are adding vector indices. And the big question is how, when you evaluate a vector database, how far along is it in adding search engine capabilities? And when you look at a traditional search engine, how seriously and how mature is their vector capabilities, because they're relatively new compared to the vector databases. So that's basically it. That's my talk. If you like this topic, I have three talks here on building a vector database from scratch that I live coded. You can find that at maven.com/softwaredoug. And yeah, that's it. And I'll hang around for a bit of questions. Thanks, everyone.
Thank you so much. Amazing. We already have one question in the chat. Daniel, what is the future of RAG? Will large context models solve for this, or will we always need vector DBs for accurate recall?
Yeah, I'm not sure, like, so people hear large context models and they think like, oh, now it's perfect at 1 million tokens. And really it's like, I see this talking to GPT-5 all the time. So first of all, GPT-5 uses up a lot of tokens in reasoning, and a lot of our models use a lot of tokens in reasoning. And things start to fall off quickly. So I asked a question recently about Charlottesville, so where I live, Charlottesville, Virginia. And it was, after a little bit, it started to think in terms of Charleston, Virginia, or Charleston, South Carolina, and Charlotte, North Carolina, like similar sounding towns. It was like finding housing data on these places, and it was like really confused. So I'm not sure that even large context models, 1 million tokens, it's not like we're going to be able to fit everything. And we're also not, maybe for a small amount of data, but we're almost never going to be able to fit all the data in to be able to like grab that. So to be able to actually solve the answers users need, we really need to winnow it down. So even if there were 1 million tokens available and it got them perfectly, almost all the time, like if you're searching Wikipedia or something, you're still going to want to like zero in on what you want, and also save token space, token cost, and latency that are going to be problems.
Great, thank you so much. Jared asked, we want to avoid using RRF. That was, I think, during the talk.
Yeah, so RRF is an averaging of two search systems' performance. It's sort of been a band-aid until vector. The reason it exists is because traditional search teams often come along and they add a vector database to a mature system. And if RRF will work fine if the vector results are of same quality as the lexical results, just different. In those cases, RRF can be valuable because they're adding to each other. But often RRF is drags if for example, you have a very heavily tuned traditional search system and you do add a vector database and assume RRF would do well, often you just average to actually worse results. The worst performing search engine that tends to drag down the performance of the better performing search engine. So I actually think it's better just to have a search system that has both lexical and vector capabilities and be able to just solve search from first principles using both of those tools instead of sort of tacking on a vector thing as a side thing.
Great, thank you so much. Any other questions? there should be a button, ask a question, where you can click in, and then you should be able to unmute yourself and ask Doug anything.
Sorry, I'll give the ask a question a try. Thank you very much for your talk. That was actually extremely good and extremely useful. Really interested in seeing some of your other talks. Where can we get those links from? Thank you.
Yeah, usually maven.com/softwaredoug, and I'll put that here. Usually that has the lightning lessons I've done. That's usually where you find me. But also Google my name and talks, and you'll probably find different YouTube videos and stuff.
We will also show, when we share the recording, we will also share these links, and we actually do also have a promotion code for Doug's courses on Maven that I will also share in the chat and then afterwards. Any other questions?
Great.
Oh,
Well,
maybe-
thanks everyone for coming. This has been a lot of fun.
Actually, another question came in. In an agentic AI world, as small language models become more relevant, how does VectorDB evolve?
Oh, that's actually a great question. I think that just makes the job harder of a vector database. We have to be able to ask vector databases more targeted questions to be really careful about overwhelming the context. This is the other end of the spectrum from if you had a million plus context window. I think like you just have to be extremely selective about the context, your context budget with these small language models. That's something really dear to my heart because I use small language. I don't not so much for agentic things, but for traditional NLP, I use small language models, and you just have to like optimize every token you give it and be really careful about that.
Thank you so much. What exactly is a lightning lesson? Do you want to take this up or?
Yeah, so it's really so Maven is a company that I do training through, and a lot of people do training through. And part of the Maven sort of formula is, so I have a paid class, and then throughout, as part of marketing for the class, but also almost like if you join my wait list for my class, it's like you're joining a meetup group where me or other people will just have talks. And so Maven kind of works this way of like encouraging you or to have lots of lightning lessons that they hope feed into paid classes, but you don't have to take a paid class. You can just come to lightning lessons and hear from people like me, or I try to host other people to give talks, and then you come ask questions. And so it's really kind of like a virtual meetup talk.
Thank you so much. Yeah, so another question. Great. Thank you, Brandon. Why should we use vector databases over traditional PostgreSQL?
Yeah, that's a great question. I don't know if you necessarily should use a different vector database. I think it completely depends on if you're happy about the capabilities of like PG Vector. I would like to know more about all the things I talked about. How well does PG Vector do metadata filtering? And then how does, I know there's PG Vector, and then there's also like a Postgres full text search plugin. I would really want to know how those interoperate with each other, or if I have to essentially treat those as separate things. So that's another thing. But yeah, you could use a lot of times the like what should I use at my company boils down to like a level of comfort and like what the team is used to managing and their experience with it, rather than like some platonic ideal, this is the best technology.
Thank you so much. Thank you so much, Kevin, for the nice comment. And yes, there will be a recording of this talk. I'm not sure if it will be available on Maven, but we will share a link to the recording afterwards. And yeah, feel free to find also Doug's course. I shared it in the chat, or find Doug on LinkedIn or any of his other social media channels.
Sounds good. Thanks,
Awesome.
everyone.
Thank you so
Take care.
much. Take
Bye.
care.